All right, good evening, everybody. Thank you for joining, and thank you for coming again if you joined us on Tuesday evening on our other middle school unit. Just to cover some housekeeping notes, I put them in the chat as well. Your videos are off. I hope that you remain muted for the duration of the webinar so we have a lot to get through in the hour. If you are a Massachusetts educator and you're here to learn a little bit about our middle school unit and the accompanying computer science modules, your attendance to this webinar makes you eligible for a free kit, a supply kit, and computer science computational tools to support your facilitation in your classroom. That does mean you have to stay for at least half of the webinar in order for us to count that, thanks to the Department of Education. They are funding the kits here to support facilitation in your classroom. So if you're in attendance, be on the lookout for an email in the next week or so with a form for you to fill out for you to select the kit you would like and how many computational tools you would like to receive as well. With that being said, what I'm going to do this evening is very similar to what I did on Tuesday. If you were here, I'm going to give us an introduction to our medicine coolers engineering unit for middle school, followed by an introduction to computer science and our computer science framework. And then I will do a walkthrough of both computer science modules. You're welcome to follow along. The links are in the chat, and I will repost them once we get to that point. That will follow up with Q&A and just wrapping up and making sure we've covered all of our bases. So with that said, I'm going to go ahead and share my screen and get us started here. All righty. So to kick us off here, I want to chat about our medicine coolers unit. So our engineering medicine coolers unit is a middle school unit, and it guides students through the engineering design process to create a medicine cooler that can keep medicine safe from high temperatures. They explore some thermal energy transfer by testing insulation materials. They also investigate a cooling solution, so there's a little chemical reaction activity in this unit as well. And they use those findings to inform their medicine cooler designs. And they walk through all steps of the engineering design process, and that results in presenting their designs, reflecting on the engineering design process. And they even get to act as users to select the most effective solution. And so what you need to know about this unit, just like all of our other units, is that it is 9 lessons long. They're approximately 45 minutes each, and I'm going to walk through what each of those lessons entails. So lesson 1 is an introduction to the engineering design process. So students are introduced to the problem by looking at this image here, which the problem is that the more you bend your head down to look at any sort of cellular device or phone, that the weight and pressure increases on your neck. They talk about whether they've experienced this problem before and how they might solve it, and they are challenged to design a cell phone stand with a limited amount of materials like cardboard, cardstock, paper clips, straws, etc., to make a cell phone stand to prop up a phone. And this is done in just a few minutes. They don't have too much time to create it, typically between 10 and 20 minutes to actually create their design. Now, this is done without introducing them to the engineering design process so that they can build up that skill set and know that they are doing engineering without that prompting, right? They can ask questions about the problem. They can plan and create a solution without being prompted so that that can build some confidence in them before you dive into the actual engineering challenge. So you are welcome to flip-flop that around. If you feel like your students might need more support, you can introduce the engineering design process to them first and then have them go through those steps as a group. Or you can do it as written, whatever works for your students. In lesson 2, this is our first part of our engineering design process, which is framing the problem. We need to look at what this problem is before we can actually dive into solving it. So in this case, they watch a video to frame their problem. of a real doctor who's based in Kenya, and he explains the problem that a lot of times in Kenya, the roads are not tarred and the treks are very long to bring medicine from one place to another. They're often put on camelback in some sort of medicine cooler. They'll pack them with ice packs, but eventually those melt and the medicine starts to go bad. They're losing their efficacy because the medicine is getting too warm. And once they're introduced to this problem via a video, they start to really evaluate what this means for a lot of people and different medications. So one of the things they do, they make a medication scale in their groups and we have a discussion. So they'll get a bunch of different medications on cards. There'll be a little bit of information about what that medication is used for and how often people use it. And they sort them by what medication they think might be the least important to keep safe to the most important. So a lot of times, it's a little small on the screen here. Students might put epinephrine up at the most important medication to keep safe because it's a life or death situation. If you don't get to use it, it could mean pretty bad things for that person. Versus pain relievers, which might be farther down the list, where you could survive without them in some cases, but in others, it might not be as important as the epinephrine, for example. The next thing they do is sort different scenarios where people might be exposed to high temperatures because it's not just in Kenya, right, where that might happen. So some of those examples might be living with air conditioning, living in a cool climate, spending a lot of time outside. Who might be least exposed to those high temperatures and who might be most exposed? The idea here is that students really consider who is most impacted by the problem so that they can really hone their solution to meet the needs of those particular people. That is followed by they're introduced to the idea that they're going to make a medicine cooler. And one of the things that can help with that are insulating materials. So they learn how coolers keep things cool in this case. So they do a test under a heat lamp. So just keep this in mind in classrooms as the heat lamps do get warm. In middle school, we haven't had an issue in our pilot test classrooms, but just keep in mind that they do get very warm. So they test different insulating materials, including the ones you see on the screen here, aluminum foil, bubble wrap, cardboard, etc., in different layers, whether that's one layer or two layers, and they record that data over the course of 5 minutes under the heat lamp. So they'll be recording every minute. So every minute they have to take a look at the temperature inside of the cooler and outside of the cooler to see which ones are slowing heat transfer the best. Generally speaking, bubble wrap is up there, cardboard is up there, lots of air and good insulators. And so they're introduced to some new vocabulary of the thermal insulators. The ones that are good are the ones that slow heat transfer the best, and the ones that are poor thermal insulators are the heat transfer is happening very, very quickly. So they use this so they know which materials to use to insulate their medicine cooler. This is followed by probably my favorite lesson as they begin to investigate more things that could help with their medicine cooler. So they know that they can use insulating materials to keep the cooler itself colder. And now they think about how can we lower the starting temperature of the cooler in the first place. So they learn that their medicine cooler will actually be a system. So they'll have both the insulating materials inside the box as well as a cold pack. And so this cold pack is just a very simple chemical reaction between potassium chloride, KCl, and water. And so students, you jigsaw this and they actually do a little bit of Google Sheets. All the Google Sheets are made for you so they can plug in their data directly and it will make their class data plot so they can all look at it. So it's a bit of a jigsaw. So all the groups will test different amounts of potassium chloride with the same amount of water. So your water will always be 30 milliliters, and then the students will test 0.5 grams in 5.5 intervals up to 10 grams of potassium chloride. And what they typically learn is that the more potassium chloride they add, the colder the cold pack was, but there's usually some sort of plateau at some point in the higher numbers where if you go past 9 milligrams, for example, you might not get the same cooling effect. So they use this knowledge to select the amount of potassium chloride they'd want to use in their cold pack for their medicine cooler. This, of course, is followed by brainstorm and plan and create. I like to combine these typically on a slide so you can see what their full criteria and constraints are. So once they've established that they want to keep medicine for cool for, excuse me, for as long as possible, slow the heat transfer in the cooler with their insulating materials, and cool the air using their cold pack, we also know that we need to hold as much medicine as possible, right? We've looked at the different medications we might want to keep safe. And so there are little sample medicine vials that they can fit inside their box to count how many fit. And then, of course, now they're introduced to their budget that they only have $9 to create their medicine cooler. And at this point, they do a brainstorm individually. This is the only time in our units where students are working individually. The idea is that if everybody comes with a brainstorm, that the planning phase is a little bit easier, where no students' ideas go left unheard because everyone has one. And that, of course, is followed by creating one formal plan that they can start with, and then they will create their medicine cooler. The test and evaluate phase actually takes a little bit of time for this unit because once they've created their medicine cooler, they actually have to test it under that heat lamp, as you can see on the right, some students are doing. They have the choice of which box size they want to use, and they have to test under the heat lamp for 10 minutes. So every minute they're looking at the temperature inside and outside of the cooler to see how well the medicine coolers are meeting their design criteria and constraints. And this helps them to evaluate their design so that they can make very specific changes to their medicine cooler so that they can make their next iteration an even bigger improvement. So, for example, you can see maybe on the evaluation here, say they spent the full $9. Maybe they want to lower their costs specifically because their medicine cooler was very expensive. Or maybe their medicine cooler, they chose the smaller box instead of the larger one. So now they're not fitting as much medication as they could have. So they have to pinpoint the exact thing they want to improve upon and really explain that in order to move into the next phase, which is, of course, iterate. They get to test a second medicine cooler design and test it again for 10 minutes under that heat lamp, recording the data every minute, every 60 seconds. So it is a very interesting process to watch. Students get pretty excited about how hot the outside of their box typically gets, and they compare that to their original design. And then in lesson 9, they actually get to pick which design they put up for sale. So this lesson is a great extension point for students. So they pick their medicine cooler that they felt worked the best between their two designs, and they actually make a for sale sign. So how much did your medicine cooler cost? How much medication did it hold? What was your coldest temperature? How long did your cooler stay cool for? And once they have this up with their own plot from all their data points that they've recorded through testing, they actually all get assigned a different user. So these are the 4 users that students would be assigned, and they actually get to go shopping for one of the medicine coolers that works the best for that particular user. So each user has different preferences and needs, which really highlights that for students that the medicine cooler might, if you've designed it to be the cheapest and hold the most amount of medicine, somebody might want this, but somebody else might not if they are looking for a medicine cooler that gets really cold instead, for example. And this is a good point to have conversations about real world engineering, that there is some sort of competition often in the end with designed products of which product might work the best for different people, and that it is often very difficult to design a solution that would meet the needs of everyone, and having those types of conversations as well. I also recommend sometimes to do the sale before you do your iterate step so that students can get a sense of who would buy their medicine cooler in order to make that improvement and sell it to more people and meet more needs of other users. And that pretty much wraps up the engineering medicine coolers unit. And this will sort of ground us in our 2 computer science modules. So I'm going to start working through these for you, but I will introduce you to these 2 CS modules. Just so you know, our CS modules for YES, Youth Engineering Solutions, really have to be paired with the engineering unit, and some of our older EIE units, they could be done separately, but these modules really accompany the engineering really well. So for example, the medicine cooler alarms, which uses microbits, which are little mini computers, are specifically made to design an alarm for the medicine cooler. So if you didn't do the engineering, it's kind of a little, it's a little less fun and plugged in for students in the same way. So the two computer science modules for medicine coolers are Heatwave Visualizations, which uses MATLAB live scripts online, free to use. There are 3 lessons. They are 45 minutes apiece. And the other one is the Med Cooler Alarms. Like I said, again, this is another 3 lesson module that are each of them are 45 minutes apiece. But before we dive into each of those, I just want to demystify some computer science terms and explain how the YES team thinks about computer science as we make these units, so that you get a better sense of what you're looking for in your students when they're doing these modules. So first and foremost, if you were here on Tuesday, this will be a review for you, so it's okay to tune out for a second here. So just what is computer science? Very, very simply, it's the way that it's how we study computers, how they work, and how we can use them to solve problems. And a lot of times we complicate computer science and it gets overwhelming. There's lots of things to cover in your classroom, but it doesn't have to be that way. So with that said, some of the things that people are looking for to cover in computer science is what we would call computational thinking, or these computational skills, right? And there are lots of these. And if you Googled computational thinking, this is kind of what you would find. You would find graphics such as these. And computational thinking is really just how computer scientists think to solve problems. And there are lots of different things that they do in order to do this, as illustrated by this diagram. So I'm going to walk through these 4 skills, and then I'll show you our framework to sort of build on that. So the first piece here is decomposition. So computer scientists really face complex problems, but instead of tackling them all at once, they use decomposition. So they're breaking down this one big task into smaller parts that are more manageable. So if you're thinking of baking a cake, for example, it involves steps like mixing ingredients, baking, decorating, and each of those is a smaller task within the larger goal. And by focusing on each piece separately, it's easier to solve the whole problem. So decomposition really helps computer scientists organize and understand even the most complicated challenges. Typically, this is followed by pattern recognition. So once that problem is broken into smaller parts, computer scientists can look for patterns, right? Pattern recognition, of course, involves grouping similar items or things and noticing trends to predict what happens next. For example, if you've seen this line of cupcakes, right, the pink, yellow, yellow, you might be able to guess what comes next. In programming, recognizing patterns really allows them to reuse solutions multiple times for similar problems and saves time, right? It helps create efficient solutions, and it helps us solve problems more effectively. Abstraction is usually the big one for people because not all ideas are important when you're solving a particular problem. So that's where abstraction will come in. And it basically means you filter out any information that's not helpful to you, right? And you can focus on what's essential to solve the problem. So, for example, if you were making a banana split, an ice cream sundae, whatever you would like, you probably don't need to know how the ingredients were grown or where they were grown in order to make that recipe, right? So in computer science, it really helps simplify problems by making them easier to solve without all the extra distractions. And last but not least, everyone's favorite, which people often look to for computer science, are algorithms. Computer scientists develop algorithms to solve problems, and it's really just a set of step-by-step instructions for completing a task. So following a recipe, for example, is an algorithm. It could help guide you step by step to the process and the end goal. And it helps computers especially perform tasks efficiently and consistently over and over and over again. Whether it's sorting data or finding the fastest route on a map, they really are how computer scientists bring solutions to life. And while all of those skills are incredibly important and essential skills for solving problems like a computer scientist, We at Yes believe there's a little bit more to it, right? And so we've developed a computer science framework to support that thinking as well as build out the next step here. So we think these skills are important, but to be effective, we think that students and people in general must also be thoughtful and conscious users of computers and computational tools. That really means thinking beyond just the mechanisms of problem solving to understand the broader understand just the mechanics of creating an algorithm or using a computer, but really thinking about problem solving to understand the implications and the impact of how we use technologies. So this framework has three components here that sort of outline those exact things. So of course, the generate and use algorithms is sort of principle. It reminds us that using these things is vital in computer science. We're not going to be able to do computer science without algorithms, really. Um, but it's not just about using those tools, it's knowing how they work in order to solve problems and create new solutions. The second there in purple is increase efficiency and accuracy, which highlights that these tools are really designed to make things faster, make things easier for humans, try to eliminate some of this human error that might happen. And of course, the last one, which is the most important to us, is in the red, is that we recognize the social context, that technology doesn't exist in a vacuum. We need to be aware of biases and how our own personal opinions, feelings, etc., how we're using a particular tool might impact the data that we get, and that could impact different solutions and how people are affected by that. So in summary, our framework really is an extension of your general computational thinking modules. And why are we even pairing these things together? Why are we doing engineering and computer science? For us, these are natural partners in solving real world problems, right? While engineering focuses specifically on designing and building solutions, computer science can enhance those processes and provide powerful tools for analysis and making things more efficient, accurate, etc. And this is why we are pairing engineering and computer science. And we hope that students will be able to see how the two disciplines work together and tackle complex challenges. So there's some examples of computational tools on the screen, which we'll actually talk about one of these in the unit. And data visualizations are really helpful for managing big pieces of data, lots and lots of data points, right? Make it easier for engineers to interpret and use in solutions. And the framework really emphasizes some of these connections as well, helping engineers and computer scientists really consider the impact of their work and trying to make it better for everyone. So what I want to do now is actually walk you through one of those computational tools here, which is our first computer science module, which is Heatwave Visualizations. The thing I want to, the code, the website is here as well, but I can put it in the chat again for everyone. All right. And so what I want to emphasize about this particular module is that it fits very squarely into the frame phase as we're thinking about what the problem is and how we can solve it. This is really framing a real world problem of medicines are going bad because the temperatures are high, and how we can use data to drive some of those insights and connect back to how we might make an even better solution. So I will head right over. When you visit the website, you will land here. So the first thing we are introducing students to in lesson 1 is just how to use this live script, because a live script is a particular programming area that has been programmed for you to use. So if you click launch there, you can see what students would see. So they need to understand what they're looking at before we get started. So when you are logging in, you would ask students to figure out what is their definition of a heat wave, right? Because this is one of the examples that might come up where other people might be affected by hot and high temperatures where medicine could go bad. So specifically, heat waves, if you plot the results here, you'll see that they're defining a heat wave as any day between May 1st and September 30th, where the high temperature was greater than 95 degrees Fahrenheit. So that's what it's counting as a heat wave day. And then you have your map here, and you might be able to ask students where the most heat wave days are happening and how they know. So they know what they're interpreting in this data set. So what you're looking for is if you see a big red dot, there are the most heat wave days. So for example, if I'm hovering over this location in California, you can see they had 134 heat wave days based on that definition. And you also have the option to zoom in. Sometimes it is a little slow with the zoom in feature, just by the way, for they were working on improving this with MathWorks themselves. But if we go to Boston, you can see with that definition, any day between May 30th and September 1st, over 95 degrees, it puts Massachusetts and Boston having 6 heat wave days. So that's really the goal here, is that they understand what they're looking at in these visualizations before they get started and dive into some other things, as well as having a discussion about this particular definition. How do we feel about this particular definition? A lot of times people are not very happy with this particular definition because usually heat waves last longer. How long is an actual heat wave? Is that span of months making any sense to us? Is 95 degrees really a heat wave if we live in Arizona, for example? So they start to have these conversations about how do we define a heat wave and who gets to make that decision. Okay, and so if you click exit in the upper right, we can launch into lesson 2. So this particular heat wave visualization, once it loads, was made using the exact same data. And if you click plot results, you're seeing an entirely different map. And yet the first map we just saw was using the same data, but these two maps are different. So now it's time to have a conversation about how this was possible. And so students actually do an unplugged activity at this point. So it's paused from our internet connectivity, and they actually create a heat wave definition for a data set of 7 days in Phoenix, Arizona. And they make up their own definition. And then they translate that definition into an algorithm and they hand that to another group. So every group gets a new set and they get to count the number of heat wave days. And what they typically notice is we've all used the same data, the same 7 days from Phoenix, Arizona, and yet so many of our groups have counted a different number of heat wave days, and they realize that their definitions were different. So if they define a heat wave differently, they're going to get a different data visualization. So in this case, in their version 2, at this point, you would tell them that they defined a heat wave differently, and that resulted in a drastically different data visualization, which could have major impacts, right? So this one defined it as when the high temperature is greater than 105 degrees for 2 consecutive days, and the low temperature is greater than 80 degrees for 2 consecutive days between the same span, May 1st and September 30th. So what they start to notice is, okay, this might be a good definition if you live in Arizona or California, but we might be missing heat waves throughout the rest of the country that could have been important because our medicine cooler could have helped them during that time period. So once they get a sense of that as well, they're noticing also that all of these visualizations are processing a lot of data. So these first two modules here in the lessons are processing over 2,300 different data points for a singular set of days. So they're like, oh, the computer can help us visualize this a lot easier than actually trying to do this by hand and look at all of these data points one by one. So at this point, you're asking your students to create their own heat wave definition for a different region of the US. You can either have them do it generally. We typically push for the region because there are 2 different things you can do in lesson 3 for that. So the first thing you can have them do, if they're choosing a region they're not from, is to launch the normal temperature patterns. which will show different data sets for different parts of the country, different regions. So they get a sense of what that part of the country might experience, generally speaking. So in the Northeast, our heat wave days are probably mostly in August, which is important for us to note, versus some other parts of the country. We can probably say that 100 degrees in Arizona is probably pretty normal, but in Massachusetts, that would be insane. So looking at the normal temperature patterns helps sort of start to frame their thinking as well about what my definition should be. And it actually plots this animation and runs it for the whole year so they can see how hot those temperatures are throughout the year. Once they've gotten a sense of their particular region, wherever they decided to pick, the Northeast, the Southeast, etc., they are able to make their own heat wave definition. If this would exit for me, that would be great. They are able to make their own definition by playing with different variables that make sense for that region, what makes sense for them, whatever their experiences might be, could be important for their heat wave definition. All right. It'll work with me eventually. All right, we'll pull this back up. All right, and so once they're in lesson 3, they can create their own definition of a specific region. And once they're in there, they can choose different variables someday. So the variables are very similar to what you had seen in the first 2 modules here. So now it doesn't want to work, but that's okay. It very simply, they get to choose the upper and lower limits. So how many days, up to 3 days consecutively. They get to choose the temperature variable. How low does the temperature have to be? How high does it have to be? And then which region are they looking at? And they're able to test various definitions in order to come up with their final definition for that particular region. Once that is complete and they have a data visualization that they feel pretty good about with their particular definition, they are able to have conversations about how their definitions might differ, how some of their personal experiences and preferences might have impacted their definition. So say you have a student who has experience living in a different part of the world. Maybe they're from South America and that experience in the hot weather could have bumped the temperature up, right? In terms of what is actually hot, what could be a heat wave. So some of those personal experiences can change the definition, as well as what you're designing your definition for. So if you were a climate scientist, you'd be looking at something entirely different than somebody who's just looking for the hot days so you can sell your medicine cooler to people who need it. So those types of conversations really come from this heatwave visualizations, talking about biases and how not all biases are actually bad. Sometimes they just influence our decisions. And it could be as simple as I prefer hot weather to cold weather, so I bumped my temperature up to 98 instead of 90. So some of those things are not always bad, but they do influence our decisions and who gets a say in defining these things. And so we can make a medicine cooler or design solutions with the data that can really support helping those people in need. So with that said, yes, please leave. We will talk a little bit about how that connects back to our framework, and then we'll move into the medicine cooler alarms. So these are the 3 guiding questions for each of those lessons. The first one is, how can visualizing heatwave data help us identify which regions and people might be most impacted by hot temperatures? Very generally speaking, this ties into a couple of those. So we want to generate and use algorithms in this way so that we can actually create the heatwave data visualization that can help us analyze that and who might be impacted the most, as well as recognizing the social context, knowing that different people might be impacted in different ways, different parts of the country, power outages, all of these things might impact who is most affected by hot temperatures when those medicines go bad. The second lesson is how can the same data be used to create different data visualizations? Very, very simply, this is about not just efficiency and accuracy, but again, recognizing social context because it highlights the need for efficient tools that can analyze all this data, and accurate representations of the data can affect decision making and understanding the scope of heat wave impacts, but then also understanding who's impacted by the changing of the data definition and who's left out and whose voices are not heard in that space. And then, of course, the last one is how does an individual's perspective influence a data visualization? And at this point, they're making their own definitions and reflecting on their own experiences that have influenced their decisions for how they defined a heat wave, and recognizing the influence of that really ensures that the visualizations are relevant to the problem here, that medicines go bad at hot temperatures, and they're designed to reflect the needs of the people who need them the most. And again, something as simple as preferring cold weather or hot weather could have influenced that decision. So with that said, let's dive into our second computer science module here, which is medicine cooler alarms, which is uses a small microbit, which you can see on the screen here inside of a medicine cooler. Just dropping the link again for everyone. Now, at this point, this particular lesson and module explores the creation of a temperature monitoring and alert system for the medicine coolers. And this is really about the improve phase and the role of automation in engineering solutions. So before we dive into the website, lesson one is a introduction to why are we even looking at this. So monitoring medicine cooler temperatures. So students are shown this particular graph and are asked to think about, will the medicine eventually warm back up? And of course, the answer to that is yes. And how do we know when to check on this medication, when to change our cool pack, and what challenges might we face when we're doing that? So, for example, if they think back to their video and they're thinking about traveling through Kenya on camelback, they might be thinking, okay, it might be kind of hard to stop and reopen the pack and fill it out on the road. It could be difficult to try to check it very, very often. So we need some sort of tool that can make this easier for us because during the testing phase, as I had mentioned, they're recording the temperature every minute for 10 minutes to see how hot the medications are getting. So it could be very tedious. So we need something to help us out here. So the guiding question is, how can we use a computer to monitor the temperature of the air inside the coolers? And they are launched to think about some other devices or apps that are always collecting data. And the reason they're able to do this is because they have a sensor, right? There's something about that device that can take inputs from the environment and send it back out, whether that's your phone or your Apple Watch, your iPad, whatever it may be. And at this point, they can see a microbit, which has built-in sensors, which can be used for this particular moment. And so what you have to, unfortunately, preload onto the microbits when you're in, my apologies for not showing you what you look at. So once you're on Make Code, you can click New Project. I have some of these pre-made for us. So you can click New Project to create this as well. So students are handed the microbits at this point, and they're instructed to press the A button. If you press the A button, something happens. In order to make this on your microbit, very simply, you're looking for an input, which is on button A. You could also choose button B. Then the show number is a blue block. It's a basic block, which you could also drop right in there. And then the last input is also in the pink. And the temperature, if you scroll down, is available there, and you can drop that right in. And you can test it very easily. Live online without the physical microbit. If you press A, something scrolls across their screen and they're asked, what are you noticing? What is it showing you? So basically what's happening here is that when button A is pressed, it's going to show you the temperature in the room currently. The other thing that they also have to know is, of course, that they just tested everything in Fahrenheit and it has to be converted to Celsius for the microbit. So they're introduced to this concept as well. The LED screen on the microbit is showing the temperature in Celsius. Now, the other thing we are introducing to them is that there is an input and an output. That on button A press is an input. We're giving the information to the computer, and then the output is the temperature. It's spitting back out the temperature once we press that button. So at this point, you would reflect on what that's telling the microbit to do. Of course, we just discussed it, so I won't relay it again. And that at this point, you can define for them that this is an algorithm. It's a set of instructions to complete a task. Now, at this point, you would give them a few minutes to play in MakeCode and navigate to the website themselves to play with inputs and outputs and let them explore a little bit. So you can change this to button B. If you press button B instead now, the temperature will scroll across. They can also change that output. Maybe they want to show an icon instead. And so now when I press button B, we're going to get a few things. We're going to get a 21 and an icon of the heart. So they get a chance to explore it a little bit to find where these blocks are, which is very, very important. There are a lot of blocks, admittedly, so it does take a little bit of time to find them all. And then at this point, they have a discussion about whether this algorithm would actually help with the medicine cooler. And usually this conversation results in, well, I have to press the button every time. Is there a way to make it do this over and over and over again? Is there a way to make it sound? So they start to have a little bit more discussion around this is probably not the most effective algorithm here. And so this is where we get into our favorite, our loops. So we want a set of instructions that are repeated, right? We don't want to have to keep checking and pressing a button and going over to the medicine cooler to press it to see what the temperature is. In order for them to understand what the loop is, there's a very simple activity on a slide where we're looking for the particular loop in this set of instructions. Read the temperature, record the temperature, wait a minute. And of course, the loop is that first section. We want that part to loop over and over and over again. So at this point, you can introduce them to our first loop block, which I will also show you in MakeCode. Nope. So this one, very, very simply, this is milliseconds over here, which is important to note for students as well, is that every 60,000 milliseconds, which is 1 minute, it will show our temperature. So over and over and over again, it will continue to show our temperature every minute. So right now, it's going to keep cycling that every minute. Again, if you're looking for the blocks, it's always by color. So our loops are green. And if you scroll down, you can find this and you can adjust the time as needed. The show number is a basic block in the blue, and our temperature is the pink input one. So once we're introduced to the loop block, there's some more reflections about how this feels versus doing it by hand. What are some of the similarities and differences? Of course, this is so much easier than recording the temperature every minute by hand. And they're thinking that, you know what, this would have been really useful when we were testing our medicine coolers. And we want to think very critically about how we can make this even better for ourselves and for our medicine cooler. So this launches us into lesson 2, where we want to actually create a medicine cooler alarm. So they return to that specific algorithm, the one we still have open over here, that every minute we're showing the temperature. And they're recognizing that this probably isn't the best either, because we want it to make an alert. We want it to sound for us to actually look at it when the temperature is too hot, too cold, etc. So we want to think about how we can create an alarm to alert users that the temperature inside their medicine cooler has gotten too warm. So they know what their loop is, and they want to also add an additional output. And so we can introduce them to the fact that there are output devices on our microbit. There's both the LED display and there's a speaker in the version 2s, which can help sound the alarm when our medicine coolers get too hot. And at this point, I can show you the output demo, which you can have one medicine cooler that's made this way, one microbit. The input, again, is just in the pink. You can change it to whatever button you would like. And then this play tone is actually just in the music. If you scroll down, play tone, middle C for 1 beat until it's done. So at this point, it'll play us a little note. And students are asked again, what is the input here? What is the output? Our input is the button A, and our output is the sound. So this might be useful for us in our med cooler alarms. And of course, the other thing students start to ask is, what temperature do medicines go bad at? Which is approximately 30 degrees Celsius. So whatever their alarm is, they might want to think about using that in their algorithm to support the best possible alarm to prevent their medicine from going bad. So at this point, they are able to write a draft of their algorithm. What do you need to tell your microbit to do in order to sound an alarm that could alert people when their medicine is going to go bad? And a lot of times what happens at this point is that they start to come up with conditionals on their own. If something happens or if something is true, please make a sound. So if the temperature gets above 30 degrees Celsius, make a sound. When the temperature gets above or is at 29 degrees, make a different sound. So all of these are conditional statements. So at this point, they get introduced to a sample alarm algorithm, which I also have made for us so that we can take a look at that as well. The loop block is the green one with the every some odd seconds. Right now it's 1,000 milliseconds. You'll be showing the number in the blue. Our inputs are both temperature. The logic button shows our if-then statement, which there are actually two that you have to add. So I'll pull those out for you to see. So it's if this little block is empty here, we need to add the greater than sign in there and change that over. And then we already knew where the music was in the red, so pull that in. And then you can change these. You can add your input temperature down here and then change your degrees there, just so you know where those logic and loops are. And at this point, we're introduced to the idea that every some odd seconds, we're going to show the temperature. But if the temperature is greater than 30, then we want to hear a tone. We need to be alerted that that is happening. And that if-then statement is one of those conditionals. So we can demonstrate what happens by actually playing with the virtual microbit here. So right now it's at 18 degrees Celsius, and I can bump it up here, and then it will eventually play. It plays me a tone that it is too hot, and it'll keep going. So I'm going to pull the temperature back down so it doesn't keep doing that to us as a background. But this is just a demo for them so that they understand that they could adapt this and add other parameters if they would like. So at this point, they're instructed to head on over to MakeCode themselves. They can test it by dragging the temperature up and down. And then they get to make their own algorithm and share that out. What are your inputs? What are your outputs? So oftentimes students will add a few things to this, like adding additional if-then statements, like if the temperature is above 25, they play a happy song, because you can add a full melody if you would like. So you can add notes and play little songs on the actual microbit for each level. So some students will really beef out this algorithm with various points so that their medicine cooler alarm alerts them when the temperature is still good, alerts them like a warning, you need to come change the cold pack now. And another one that might have a Jaws theme, I've heard some dun dun duns, like your medicine is now expired. So they can change that by changing the temperature and adding additional if-then statements in to their algorithm. So it is quite a bit of fun, and you actually can test these directly in your medicine coolers. You can test them directly under a heat lamp with the physical microbit that can be unplugged from the computer. In order to do that, Just know that you will need the USB that comes with the microbit as well as the battery pack that comes with the microbit as well. In order to download a specific code onto a microbit, you have to have it plugged in and click this download button here. And then at that point, you can unplug the microbit, plug it into a battery pack, and use it throughout your classroom under a heat lamp, etc. So with that said, after that, they get to reflect on some of the advantages and disadvantages of using the particular microbit. Are there disadvantages? Like what happens if the battery dies on the microbit? Or, what happens if the weather's too hot and now the microbit's not working, because that happens with cell phones sometimes. So really reflecting on, are computers always the best solution for everything? Um, Again, and then there's some reflection on if we messed up and put the wrong degrees, like if we did Fahrenheit instead of Celsius, knowing that we might have human error like that in a code, knowing that that would impact our designs and that our medicine might go bad in that case. And then, of course, do you think that it's important for the loop in the medicine cooler alarm to check the temperature every second? Typically, the answer to this is no. Maybe the temperature doesn't change that drastically that quickly, and having some conversations around that. And then last but not least, the extension questions are it's important to think about how often our data is collected for a device like a medicine cooler. Um, and in this context, it should be considered because we don't need to have the algorithm looping every second. But maybe we need to think about how often our other devices collect our data, which devices should be collecting data more often. Um, for example, your Apple Watch might be detecting your heart rate, and that could be really important. I know that feature has saved people's lives in the past, but for other things, just like tracking your location and other things, what is what are the limits of collecting data and some of those inputs and outputs on our actual lives? So this extension is totally optional for conversations in your class and where your students sort of stand with that. So I won't run through these here specifically because I talked about our guiding questions quite a bit. We really try to tackle all three of these domains, especially the social context. What does it mean for us to collect this data and etc.